Alright, so in this problem we're trying to find the area enclosed by a parametric curve and the y-axis. And here are the two formulas written in orange depending if it's enclosed by the y-axis or the x-axis. So in this case we're going to be using this one. I do want to give a little bit of background as to how you might get to that just using basic principles of integration used in previous chapters without necessarily remembering it. So to do that, I'm just going to look at this case for this one, but it's very similar for the x-axis, something enclosed by the x-axis. So let's just look at some function x of y, right? And then we're trying to find the area enclosed by the y-axis. And this is kind of a standard problem. You'd find a curve, right? And then it would go from A to B on the y-axis. And then you would say, okay, well, we can find the height at each value of x, and that's just each value of y, and that's just modeled x of y. And then we'd just partition the y-axis, sum up all those heights, multiply by the base, and we'd get this. A to B, x of y dy. So that's just a standard integral to find this area. Now, how does that relate to this? Well, if we consider x to be the height, right, in this case, in the parametric case, we also have x explicitly as a function of t, which is just called g of t. So it doesn't really matter what x is a function of. If it's describing the height, it's describing the height of this at each point. So in this case, it's going to be at each point of t. So we have to keep that in mind. But g of t is really the same purpose as x of y. Same thing, just different variable. And then dy, well, generally we're given a parametric function, right? We're given y as a function of t as well. So if we wanted our dy, and you could think back to maybe u substitution, it's very similar. You're just going to differentiate both sides, and then you get dy is equal to f prime of t dt. So then that's f prime of t dt. And then that's going to be your differential, and it's going to be in terms of t now. So you basically have everything that you need, and the last part really is just the bounds. Instead of a and b, it's just traditional to write alpha and beta because we're describing now t values. And this, in the case of the y-axis, is going to be where the x function of t is equal to 0. And then from there, that's how you get this formula if you were just to look. So I would just recommend drawing a little diagram and trying to work it from there. It's not too difficult. So let's actually just use the formula now on this specific problem. So first thing we need to do is figure out our limits of integration, alpha and beta. And if we're doing the y-axis, right, enclosed by the y-axis, we know it's when x function is equal to 0. So x of t is equal to 0. And in this case, our x of t is 2t squared. T squared minus 2t equals 0. And that, we can factor out a t and get t equals 0 and t equals 2. So those are our limits of integration, alpha and beta. So let's just write that down. 0, 2. Our g of t, well, that's just our function of x. X is a function of t, so that's just our t squared minus 2t, not a problem. And our dy, well, we wrote that's f prime t dt, and so we're going to differentiate root t, that's our f. So the derivative of that is 1 over 2 root t dt. So now we've got our integral, and the last subtlety we have to worry about is in this diagram, I drew it on the right side of the axis, but we don't necessarily know that. It could be entirely over here, but it's either one or the other, because if you look at it, it's only intersecting at 2 points on the diagram. So if there's a value, let's say x is negative here at t equals something, right, between the two values, it's going to be entirely negative. There's no way it can intersect and flip because there's only 2 points of intersection. So we just have to test one point, and if it's negative, all we're going to do is throw in a negative sign for this integral, and that's basically just saying that the upper curve, so to speak, is the y-axis, and the lower curve is our function. And if you remember, we do upper minus lower when integrating. So in the case where x equals 0 is our upper, we just get a negative function. And if it's on the right side, we just have our f of x minus 0 is just f of x. So that little subtlety is important. And if you didn't do that, it's fine. It's just at the end you get a negative value and it's supposed to be positive. But the actual value is the same in absolute value. So let's just test a point. Let's just test x equals 1. Well, t equals 1, x of 1. So we're just plugging in 1 into this function. And we get a negative value. So it is indeed on the left, and we have to throw in that negative sign. And that completes the setup. And then from there, it's really just integrating. So what I'm going to do is factor in this negative onto both terms and factor that in to both terms as well. So I'm going to get 0 to 2, 2t minus t squared over 2 root 2 over 2 root 2 dt. And then from there, 0 to 2, that just simplifies to root t minus t to the 3 halves over 2 dt. Okay, we can integrate that. We'd get 2/3 t to the 1/2 minus 1/5 t to the 5 halves from 0 to 2. And then we just plug in our 2. Oops, this is a 3. Adding 1 to the exponent here. So then we'd have 2/3, and then 2 to the 3 halves is root 8, and that's the same as 2 root 2. And then from here, plug in 2 to the 5 halves. Well, 2 to the 5th is 32, so root 32, and that can be written as 4 root 2. Okay? So we're getting 4 root 2 over 3 minus 4 root 2 over 5, which is the same as, let's just find a common denominator, 20 minus 12 root 2 over 15. So our final answer is going to be 8 root 2 over 15. And there you go, and that's how you find area enclosed by parametric functions.